Hi, we present PlatoNeRF, 3D reconstruction in Plato's cave via single-view, two-bounce Lidar. PlatoNeRF is named after the allegory of Plato's cave, in which reality is discerned from shadows cast on a cave wall. 3D reconstruction from a single view is challenging due to ambiguities in monocular cues and occlusions. We propose combining the benefits of Nerf and two-bounce light measured with a single photon LiDAR to enable single-view 3D reconstruction. We find that these methods are complementary. LiDAR data can address the challenges in single-view Nerf, and Nerf can address challenges in 3D reconstruction with LiDAR data. In particular, using LiDAR enables shadows that reveal occluded geometry to be measured, even in ambient light and low albedo backgrounds, whereas detection of these shadows in RGB images, such as those shown here, becomes more challenging under such conditions. Using Nerf enables smooth interpolation of geometry when constrained to the low spatial and temporal resolution LiDARs found on consumer devices. Our method works as follows. We illuminate individual points in the scene one at a time by scanning a pulsed laser. This light diffusely reflects in all directions when it hits a surface in the scene. The reflected light acts as a virtual light source, illuminating the rest of the scene and casting shadows. Light that returns to the LiDAR, which is kept stationary, provides information about the visible scene, while pixels that lie in shadow provide information about occluded parts of the scene. We capture a 3D time-of-flight image for each scene point that is illuminated, and use this data to train Nerf to learn the entire scene's 3D geometry. To learn 3D scene geometry, our method is trained to reconstruct the two-bounce time-of-flight, where bounce refers to the number of times that light reflects off a surface, with one bounce light shown here, and two bounce light shown here. The time of flight of two bounce light is related to the distances over three rays shown here with D1, D2, and D3. The ground truth two bounce time of flight is indicated by the peak in the transient image captured by the LiDAR for each pixel as shown here. This so-called transient contains photon intensity over time for a given pixel. To reconstruct the two bounce time of flight, we must predict two quantities. First, whether two bounce light is measured at a given pixel based on whether or not it is in shadow, and second, if two bounce light is measured, its time of flight. To estimate these quantities, we trace rays in reverse. Primary rays are traced from the sensor to the scene and used to estimate the time of flight of two bounce light. Secondary rays are traced from the termination points of the primary rays to the virtual light source and used to estimate whether pixels are in shadow. Intuitively, if a pixel is in shadow, an opaque object must lie between the virtual light source and the measured point in the scene. Our method involves three steps. First, we use Nerf to estimate the depth along primary rays. Depth is volumetrically rendered based on the predicted density of sampled points along the primary rays. Predicted depth is used to compute a predicted two-bounce time of flight, which is compared to the ground truth extracted from the raw LiDAR measurements. Next, we volumetrically render transmittance along secondary rays by sampling points along these rays and again predicting their density. The final transmittance along the secondary rays is a predicted probability of the corresponding pixel not lying in shadow, which is then compared to the ground truth shadow mask extracted from the raw LiDAR measurements. Finally, once trained, we densely query the Nerf model to estimate density throughout the scene and use this density for 3D reconstruction. We create a dataset of simulated scenes captured with both a single photon LiDAR and RGB camera to evaluate our method and compare it to past work. The simulated scenes are shown here, with the lower images being the train views and the upper image being example test views. These datasets will be made public to accelerate future work in this area. We compare our methods with a single-view LiDAR method called bounce flash LiDAR and a single-view RGB Nerf method called S3Nerf. Results for PlatoNeRF, bounce flash LiDAR, and S3Nerf are shown here from left to right. We see that PlatoNeRF is able to recover more details without over-smoothing, as is further supported by the metrics reported in the paper. We also ablate performance under several conditions, such as reduced LiDAR spatial and temporal resolution, ambient light, low albedo backgrounds, varying number of illumination points, and non-planar background geometry. Results indicate that PlatoNeRF is more robust to reduced spatial and temporal resolution than LiDAR-based methods like bounce flash LiDAR, and more robust to ambient light and low albedo backgrounds than RGB-based methods like S3Nerf. Lastly, we demonstrate reconstruction on a real-world scene as shown here. Results are promising and indicate that PlatoNeRF can accurately reconstruct scenes measured with real LiDAR data with fewer artifacts than past work such as bounce flash LiDAR. More details can be found in the paper. Thank you.